Hi everyone, I'm excited to present this tutorial on using pediatric fee codes for electronic health records phenotyping. While the original fee codes are great for analyses using or in adult populations or general population level analyses, there's specific adaptations required for pediatric research, which is why we developed the pediatric fee codes or Peds-Phecodes from the existing fee codes. But in this tutorial, we'll walk through how to use the Peds-PheCodes package to map ICD codes to pediatric fee codes, and then run a phenome-wide association study, or PheWAS, using some simulated data. But with that, I'll get started. Here I have some brief installation instructions. For the purposes of this tutorial, all of the packages have been installed, but in order to install the Peds-PheCodes package from GitHub, you would first install the required dependencies and then the package itself. In order to map ICD codes to the pediatric fee codes and run the phenome-wide association study, the package requires 3 specific input data frames, all with a kind of linked by a shared patient ID. And I'll walk through the format below. But first, you need a data frame that has the patient diagnosis codes, and the columns needed here, which I can show in an example, would be, as I mentioned, the unique patient identifier that would match across the 3 data frames, the vocabulary ID, which specifies the coding system that the codes are mapped in, which would be, for example, ICD-9-CM or ICD-10-CM. The fee codes also account for SNOMED diagnosis codes, so those could be used as well. And then the code itself, remembering to keep leading zeros if needed, and then some sort of count or index, which either reflects the number of code occurrences for that specific code for that patient, or unique dates of code occurrence are also used. The second data frame is really just a data frame, as I'll show here, with the patient identifier again, and then the patient sex. This is primarily needed to apply sex restrictions for specific fee codes. For example, certain fee codes or phenotypes like ovarian cysts would only apply to kind of biological sex females. So that's the reason that we have this applied here. And then the last data frame that's required is your predictor variable, which is usually a genetic variant, but it could also be virtually anything. But again, this would require the patient identifier and then the predictor for that patient. So in this example here, we just have RS example as our SNP that we're using in this PheWAS. And then the first part of the workflow is condensing and aggregating the ICD codes to pediatric fee codes, which is done by this create ped phenotypes function. And then we'll give you a specific Boolean phenotype matrix as the output. So this will show you what phenotypes represented using fee codes all the patients in your data set have. And so I'll run an example here. Sometimes it can take a little bit, but you'll see kind of the output is, again, the patient identifier, and then a bunch of columns with 1 column per pediatric fee code. And then importantly, within each fee code column, you can see whether that patient has a particular phenotype based on kind of if it's true or false in that cell. And right now we have a lot of controls, but if you go through far enough, you'll see that there's some cases as well. And then the NA values here specifically refer to excluded patients that are not eligible to serve as cases or controls, either because they have, for example, they're falling within the sex exclusions, or they have a phenotype that's very similar to the phenotype that's being investigated, for example, kind of ulcerative colitis and Crohn's disease. And if you have one or the other, you're not eligible to serve as a case or control for the other. And then after you've run that and you have your Boolean matrix, the next step is really just joining that Boolean matrix with the phenotypes with the predictor that you're using, which again, in this case, is a genetic variant. And if you had any covariates, such as age, kind of principal components for genetic ancestry or anything else that you want to control for in the phenome-wide association study, then you would also join that to the phenotype matrix. But for simplicity purposes, I have not done that here. But again, kind of you see the main difference between this data frame compared to the previous one is just that we have now our predictor here, along with the phenotype status for all of the patients in the data set. And then finally, you're able to actually perform the phenome-wide association study, and this is testing for associations between the genetic variant or other predictor and kind of all phenotypes assessed using the phe codes that were represented in your patient population. And so when you run this PheWAS, you're using the PheWAS-ext function, and it's taking in the phenotypes, which I've extracted here just from the previous data frame. So that's just a kind of matrix or a character vector with the phenotype names, and then our predictor, and then we'll see what the results. This can also take some time. But here it's outputting kind of the phenotypes represented using phe codes. Again, no covariates, but then their effect sizes with their beta coefficient, the odds ratio, their standard error, and the p-value. And then you can also see the number of total patients used in that association test, the number of cases, the number of controls. And here, specifically, it's people who kind of have the genetic variant, are not excluded, number of cases, number of controls. And then perhaps the most exciting part is finally being able to visualize the results and see interesting associations. And you can do this with the plot Manhattan function, which then shows, as you can see here, this Manhattan plot with the x-axis showing the phe codes, this time colored by disease category. So for example, phe codes relating to infection are all grouped together, relating to cancer, endocrine and metabolic disorders, and so on. And then on the y-axis, you have the statistical significance, which is shown as the negative log 10 p-value of the association between the genetic variant that we were using the RS example and the phe code. And then here, I've kind of shown how you could annotate some of the phe codes that, for example, fall below a certain p-value threshold. So here we can see that this RS example SNP is associated with decreased risk of rheumatoid arthritis and other inflammatory polyarthropathies. And then it's kind of child phe code, juvenile rheumatoid arthritis. But you can also kind of manually specify which phe codes you would want to spotlight. So here I've just focused on this rheumatoid arthritis and other inflammatory polyarthropathies. But that's the overall workflow, again, going from your 3 input data frames, mapping the diagnosis codes that you have for patients to phe codes, again, which applies the exclusion criteria within the phe codes themselves, as well as any sex-specific phe code exclusions, and then preparing the data for PheWAS, running the PheWAS, and then plotting the results. You can also browse a more complete data frame with the pediatric phe codes, showing what phe codes exist, their description, what ICD codes are mapped to them here at this website, and get a better sense of exactly how that mapping looks like. And then other references are kind of details about how we created the Peds-Phecodes from the original phe codes in this paper, as well as references on the original phe codes and the original PheWAS R package, which the Peds-PheWAS R package is based on. But with that, that concludes the tutorial, and hopefully now you have a good understanding of how you could use the Peds-Phecodes for your own research purposes.